I don't know how many of you saw the motion picture Contact, Carl Sagan's novel about the discovery, the exploration of extraterrestrial life, extraterrestrial intelligence. The core of that movie, at least from my perspective, and I'm not going to do a Siskel and Ebert thing here, but from my perspective, that was a wonderful look at the conflicts, in particular, that one person had between belief system and science. Jodie Foster, who played the role, just a wonderful film. I must have seen it 5 times, and I would love to see it again. Just a terrific film, and it really gave me a perspective about how we as humans perform this battle inside of our heads and inside of our hearts. Well, tonight's speaker has a wonderfully rich background in both science and theology. George Coyne received his bachelor's degree in mathematics and his licentiate in philosophy from Fordham University in 1958, and his doctorate in astronomy from Georgetown University in 1962. 3 years later, he was ordained a Roman Catholic priest. He joined the Vatican Observatory as an astronomer in 1969, and the following year became assistant professor at the University of Arizona's Lunar and Planetary Laboratory. In 1978, Coyne became director of the Vatican Observatory, as well as associate director of the University of Arizona's Stewart Observatory. As director of the Vatican Observatory, he's been a driving force in several new educational and research initiatives. He now spends about 5 months a year in Tucson as an adjunct professor at the University of Arizona's Astronomy Department. Coyne's research to date has included studies of the interstellar medium, stars with extended atmospheres, Seyfert galaxies, and cataclysmic binary stars. One of his current research interests, which relates somewhat to our topic this evening, is a search for disks of dust and gas surrounding very young stars, disks that might signal the birth of planetary systems among the stars. Please join me in welcoming our very distinguished guest this evening, Father George Coyne.
This is only water, folks, I promise. I'll take care of it afterwards. When Dennis invited me to this, I appreciated that it would involve a little bit of work to try and organize this talk. And work is not my great forte. You know, I work for the Vatican and in Italy, and work means a different thing there than it does to we Americans, you know. In fact, when I first went over there, Pope John the 23rd, you know, he was the roly-poly, very jolly Pope who opened the windows of the church, by the way. He's the one that called the Ecumenical Council, the Second Vatican Council. Well, Pope John is elected Pope, and he comes from Venice. Well, to the people in Rome and places like that, Venice is a beautiful city, the opening to the Orient, etc. But to them, it's a little country town up there in northern Italy, you know. And Pope John had not grown up in the Vatican as most popes have. You know, he didn't move up through the government system, so to speak, so he didn't know a great deal about the Vatican. But journalists always ask the most important questions first, so they say, Your Holiness, how many windows in the Papal Palace? Well, he didn't know, but they say, how many people work in the Vatican? Well, he didn't know that either. He'd only been there 2 weeks. But he did have an answer. He said, how many people work in the Vatican? He said, about half. And then he topped that one off. I'm going to get more serious in a moment, but let me finish this. He topped that one off by the Queen of England. Queen Elizabeth was coming over for a state visit. And there was no channel there was no channel tunnel in those days, etc. So she's coming across by boat and talking to her advisors and getting ready for this meeting with the Pope. And she says, I heard that they don't work in the Vatican in the afternoon. Well, her advisors say, yes, Your Highness, that's true. And as a matter of fact, our staff come at 7 a.m., and at 2 p.m. they go off and have spaghetti and wine and sleep and play tennis and whatever. So she says, my goodness, all the problems we're already having in Britain with, shorter work week, more benefits. I mean, the prestige of the Vatican, if the word gets back that they don't work in the afternoon, I mean, we're in trouble. Do you think I could talk to the Pope about this? Well, of course, Your Highness, that's why you're going, but do it delicately, So they're having their one-on-one conversation, and she finally gets up the courage, and she says, Your Holiness, I've heard that they don't work in the Vatican in the afternoon. And John the 23rd looks at her and he says, Your Supreme Highness, that's not true at all. They don't work in the morning. They don't come in the afternoon. So that's why when Dennis asked me to come here, I knew I'd have to overcome this fear of work. But I have tried to organize what I call a little trip for you. It's a journey. It really is a journey. It's a strange kind of journey because it's a journey out into space. And the journey out into space is intended to provoke in you and in me, as a matter of fact, some, at least to my satisfaction to today, some unanswerable questions which seem to go beyond the realm of science, whether they actually do is something that I leave to your judgment and that of others. But the journey has that purpose, to kind of provoke some questions that may go beyond what science can actually answer. And so let's begin that journey. I'm going to do it actually with a series of slides. And I know when I was a child and learning how to fish, never did succeed very well, but I did learn some tricks from my grandfather as to how to put the bait on. And so I've always found it helpful when I want to do something like this to look back. What did the people in the past think about the things we think about today? Even if they didn't think correctly according to what we know today, their approach to things is always helpful for us. So I'm going to go way back to about 5,000 to 6,000 years before the birth of Christ. Okay, this is well before the prophet Abraham to locate it. Okay, in the age of the universe, as you'll see in a moment, it's not very long, but it's Stonehenge. It's a megalithic monument in the plains, the Salisbury plains of Great Britain. And the reason I show it is because our ancestors saw here, they placed here these rocks in certain positions so that they could observe the sky. This is an observatory. It's a very primitive observatory, but it's well known the alignment of these rocks is such that they would study when does the sun rise at the beginning of spring, how high does the sun get in the sky at their latitude, and they studied the sky with this observatory in order to live better on the surface of the earth. Now get the point. They were studying the heavens, but not to understand the heavens so much as to live better on the surface of the earth. It was kind of a utilitarian approach to the heavens. But at the same time, at this observatory and on these rocks, they offered sacrifices to their gods. Now that to me is already a very interesting idea, that this one and the same place, this one and the same setup of these rocks serves two purposes. Observe the skies, not so much to understand what makes things tick there, but to live better on the surface of the earth. Nonetheless, to observe the skies, but at the same time to offer worship. It's a temple and an observatory at one and the same time. Well, if that is the case, where were their gods? Well, their gods were in the sky. When they looked up at the sky, they saw these bright stars, and they linked them up in their imagination, and they created figures in the heavens. Well, we know today that this star here has nothing to do with that star there. In fact, some of these stars are more distant than other stars by thousands, if not millions of times. We see all these stars as if they're at the same distance. But they're at various distances, many of them much more distant than the screen, many of them only at the distance of the screen. But nonetheless, our ancestors didn't know that. They linked up these stars and they saw their hero, the great hunter in the sky. This is the constellation of Orion that most of you know very well, I'm sure. And if you could look over here, you'd see the bear he's hunting. And if you could look down in there, you'd see the little hunting dog that's following him. Their great hero, after all, they had to live by hunting. So this was one of their great heroes, so to speak, their god. If we today look at Orion, and especially at this part of Orion, his paunch, so to speak, what do we see? We see boiling gas and dust. And if we look at even a higher resolution, we see these incandescent areas. This is right in the paunch of Orion. What are these incandescent areas? What is all this, what appears to be boiling gas? What is that? And if we look even closer with Hubble Space Telescope, at very high resolution, we see these strings of gas, and the color scheme here is that the blue is the hottest gas and the red is the cooler gas. And you can see that there's some mixture, but they're fairly well separated. What is this all about? Well, what this is all about requires us to think about a galaxy. This is a galaxy. What I mean by a galaxy is a system of about 100 billion stars. That's one with 11 zeros behind it, 100 billion stars. And it measures 100,000 light years across. So if you light a candle here or a flashlight and your friend is here, he has to wait 100,000 years to see that light because light travels at a finite velocity. Now let's get something very simple concept but settled right away. We never see anything as it is. And that's not a philosophical statement because I'm not a philosopher. It's simply saying the finite velocity of light. Light travels very fast, but at a finite speed. So I don't see the young folks in the front row here as they are, but as they were a millisecond ago. And I don't see the Mary back there, the projectionist, as she is now, but as she was a millisecond ago. I don't see the moon as it is, but as it was 8 seconds ago. The sun as it was approximately 8 minutes ago. The center of our galaxy as it was 30,000 years ago. And the nearest galaxy to ours as it was 2 million years ago, etc. The further out we look in space, the further back in time we're looking. Because light has to travel to us from those very distant objects, traveling very fast, but at a finite velocity. That's a galaxy. Now, if we look at a galaxy in a different perspective, we see this. Now, this galaxy and this galaxy are identical. It's not the same galaxy, but they have the same appearance. But a galaxy is a very flattened system. So if we look at it edge on, we see it more or less this way. But if we turn it around by 90 degrees, then we're looking pole on, and we see these beautiful spiral arms. Now, if this were our galaxy, our Milky Way, see, the Milky Way is nothing else. We're in the galaxy, and we're looking out across the sky, so that that belt of light across the sky is the plane of our galaxy. It's the equator, so to speak, of our galaxy that we're looking at. If this were our galaxy, the sun would be about here. One of 100 billion stars, okay, at the edge of a spiral arm at about 2/3 of the distance from the nucleus of our galaxy, about 30,000 light years from the nucleus. Well, when we look in the plane of our galaxy, we see what we saw on the previous slides. We see this boiling gas and dust in various formations. In fact, here is a mosaic taken in infrared light of the equatorial plane of our galaxy. Okay? These are satellite photographs put together in a mosaic. And look at this. These knots of very incandescent gas. Why am I insisting on this hot gas and cool gas? The next slide, you see in optical light what you saw on the previous slide in infrared light, but it's just a little piece of it. Now in optical light. And what's happening here? Why is this zone dark? Is that because stars are lacking there? And look at all the stars are so dense here that we can't even resolve the individual stars. This is a part of the 100 billion stars in our galaxy. Okay? But why do we have these dark lanes? What is that all about? Well, here's a very beautiful picture of what is called the North American Nebula, for obvious reasons. Here's Florida, little fogged over. Here's the Gulf of Mexico. Here's the Yucatan Peninsula. And here's the greatest bay in the world, Chesapeake Bay. I happen to be born in Baltimore, Maryland there. California didn't exist yet. What are these large dark areas all about? Is this a lack of stars? Absolutely not. What it is that a veil of gas and dust, a curtain of gas and dust, is hiding the stars that are on, so to speak, the other side of this screen. And it's precisely that gas and dust that is going to form new stars. How does a star come to be? A bundle of gas and dust in our galaxy begins to collapse due to gravity. Normal laws of physics. As it collapses, it heats up. As it collapses, there's an interplay between gravity and magnetic fields and other disturbances, and the cloud begins to fragment. And the little fragments begin to collapse until the temperature rises. Whenever a gas collapses, the temperature rises, and when it expands, play with your toy balloon and you'll see this. When it expands, it cools down. Okay? So this collapsing cloud is so massive, it's something like 10 to 100 times the mass of the sun collapsing in, that it raises the temperature inside that cloud to millions of degrees, and it starts a thermonuclear furnace. A natural atom bomb. It converts hydrogen to helium, helium to lithium, lithium to carbon, carbon to oxygen, and on up the periodic table until you get heavy elements like iron. And once that thermonuclear furnace starts, you have a star. That's what a star is. That's why it radiates. It has this thermonuclear energy due to the increased heat from the collapse of the cloud of gas and dust. That's how a star forms. Now, I'm waving my hands and you're saying he doesn't know what he's talking about. Here is a beautiful dark cloud in which, when we examine these little globules at the edges of this cloud, we can identify them, and I can assure you of this, we can identify them as stars being born. I identify them because I can tell their surface temperature and their mass by the laws of physics. And I can tell that they're very young stars. Furthermore, here are some good examples of exactly what I'm talking about. What a beautiful picture of a cloud of gas that is fragmenting, it's breaking up. Okay, in this case, this is the hotter gas. We can color code these as we like. And this is actually the cooler gas. In fact, it's reflecting light from stars that are born and embedded in this cloud here. A beautiful example of stars being born. There's another example. Look at how this is breaking up into different zones. And in this cloud, about a family of some 100, if not hundreds of stars are being born together as a family at the same time from this one cloud. So stars are born in our galaxy and in other galaxies. What is this? This is a dying star. This is a star that at the end of its life, it could no longer stay stable, so it exploded in a very nice symmetrical way. It blew off its outer atmosphere, and that's going to expand into the universe. And this star in here is going to continue to collapse until it has no thermonuclear furnace. It cannot turn on the thermonuclear process anymore. Do you see there's a limited amount of material to burn, so to speak? There's a limited amount of hydrogen. The hydrogen becomes helium, then the helium becomes carbon. Finally, at the end, there's no more thermonuclear process that the star can turn on. It cannot, therefore, have energy to keep the outer parts of the atmosphere from collapsing, and it collapses in a final swan song and dies, and gives off this gas to the universe. Here is a beautiful example of a star dying. Look how symmetrical that was. It's like an artist painted that. But that's a real photograph of a real dying star. Okay? What is this? This is another dying star, but it looks very different than this. And the reason is this star was so massive, like 4 to 5 times the mass of the sun, that it did not die quietly, like the sun will, as a matter of fact, like these stars did, very quiet swan song, and die. Leave this matter to the universe. But this star dies violently. This is a supernova explosion. This is the famous Crab Nebula, observed by the Chinese, recorded in their diaries, so to speak, happened in the year 1054. And we know from studying the star in here that it's a neutron star, it's a dead star, and that this material is expanding. In fact, if we measure the velocity of this gas and trace it back, we trace it back to the year 1054. The gas that's here now was here then in the year 1054. So we have very good evidence that this gas is expanding from a dying star. Now, why am I talking about the birth and death of stars? The reason I'm talking about it is because you and I are here. And you and I would not be here if this process did not take place in the universe. And that is not a romantic statement. That is a scientific statement. You and I would not be here if stars were not born and die. That's a simple fact. Here is the Veil Nebula, which is what this will be in another several hundred of millions of years. In other words, this, in its expansion, will become something like this. We can't observe this process in a human lifetime. The birth and death of a star takes, a star like the sun, it took it 7 to 10 million years to be born. It's lived 4.5 to 5 billion years, and it has another 5 billion years before it will die. So, when it dies, we obviously will die. 5 billion years left, folks. There's still time to go to church if you need to and all that stuff. Don't get alarmed. But the point is, no astronomer lives long enough to see this whole process in any one object, but we can see different objects at different stages of this and piece together the process. Now, why did I say that we would not be here? This is a very important point for my purpose tonight. There is no way to get anything heavier than hydrogen except through a star. Except in the early universe was so hot at the time of the Big Bang, and we can get back to that if you care to. It's not really my topic tonight as such, the Big Bang. But the universe at its early stage was like a star, the interior of a star. It was so hot. So it, before it expanded, converted some hydrogen to helium, but very little. In fact, that's one piece of evidence that supports the Big Bang theory. Where did this extra helium come from that was not made in stars? See, you don't believe me, but we can measure the total amount of helium in the universe. And we can measure the total amount of helium that's made by all the stars in the universe, and we find that the amount of helium in the universe is more than that could be made by all the stars. And that's evidence that the universe was very hot at its beginning and made some helium. But that's a side point. My point is the following. The carbon and oxygen and lithium and silicon and whatever else you have in your earlobes and your fingernails came through stars. It took 3 generations of stars to establish the chemical abundance to make a human organism. The amount of carbon necessary, the amount of silicon necessary, the amount of oxygen and nitrogen necessary, took 3 generations of stars. What am I talking about, generations of stars? Do you see? A star is born and it dies, and it spews out this material to the universe. But now this material becomes the seeding ground, the nursery, for another generation of stars. This material begins to collapse, okay, and form another generation of stars. But now this next generation of stars is formed not from pure hydrogen, but from enriched material, because it's been through a star. So each generation of stars is made of heavier and heavier elements. It's an inevitable process. And in fact, you can say, if you understand correctly what you're saying, that the universe is getting heavier. I don't mean that the total mass of the universe is changing, but the mass is being redistributed from lighter elements to heavier elements as the universe goes on, as stars are born and they die. Now, this is fine. With Hubble Space Telescope, we've been able to get very high-resolution photographs of some very distant galaxies. Hubble has observed galaxies at a distance of 8 to 10 billion light years. Okay, that's, according to our best estimate, about 2/3 of the way back to the Big Bang. Recall what I said. When we look out in distance, we're looking back in time. So we're seeing these galaxies as they were when they were very young, 10 billion light years ago. They were just born out of from the Big Bang after the universe expanded and cooled down enough. They're newborn galaxies. So the further out we look, the younger the galaxies we see. And we see in these young galaxies, here's a Hubble photograph of that very small region there. We see stars being born in this gas and dust at rates 10 to 100 times the rate of star formation in our galaxy. In other words, there's some indication that in the early universe, stars were born and died much more rapidly than is happening, at least in our own galaxy today. So this process of making the universe heavier had a faster rate at the beginning than it does now, but it's still continuing. Here is another good example of a Hubble Space Telescope photograph of what we call star-burst regions. Regions where stars are being born at a burst. Now, I'm leaping way ahead, but we know that around some stars, planets are born. And we think we know the process. At least we know that it happened by normal physical laws. It didn't happen by a miracle. A star is born. Do you see, as this cloud collapses to form the star, okay, as anything collapses, it has to begin to rotate to conserve angular momentum. Laws of physics, simple laws of physics. But as it rotates, it flattens. So the material that's left over from the formation of the star forms into a disk. See, this is a somewhat chaotic process. I describe it as if it were a simple process. Material collapses and forms a star, but it's somewhat chaotic. Not all of the material falls in to form the star. Some of it's left over. It forms into a disk. That disk is rotating. Particles within that disk collide with one another, and they begin to build up like snowballs. They begin to aggregate until you form planets. Now, I'm not saying we know this whole process thoroughly, but we're absolutely sure that something like this happened in the formation of our own planetary system. So, an obvious question for a scientist, for anyone to ask, did this happen around other stars? I mean, there are 100 billion stars in our galaxy. There are 100 billion galaxies in the universe. So there is one with 22 zeros behind it, stars in the universe. Give or take a few million. Okay? So, and the sun is a normal star. It's middle-aged, okay? It's normal mass, etc. So 30% of the stars in the universe are like the sun. 40%, 20%. You know, you take it, but it's got to be a reasonable percent because the star is a normal, the sun is a normal star. I mean, it's like, you know, looking in this room and saying, how many people here are, you know, under 10 days old? I don't think anyone. I haven't heard any crying yet. You know, how many are over 80 years old? How many, you know, from the nature of this evening, I bet, you know, you could get some idea that 30% of the people here are between 30 and 60 years old, or something like that. You can make a reasonable estimate, right? That's all I'm doing. So this process of forming planets must have happened around some other stars. And here are, just to show you what we're up to, are the nearest stars to the sun that we're examining to see if they have planetary systems. And within the past 15 years, we have discovered of the order of 20 to 25 planets about other stars. None of them are like the Earth because we don't have the technology to detect a planet like the Earth, even about the nearest star. We're very limited in our technology. But we have detected planets about other stars. And not only that, and much more thrilling to me, is we've observed protoplanetary disks about stars. That is, stars that have these disks that I've been shouting about. The planetary system was born in. And here's some pictures. These are Hubble Space Telescope photos of stars embedded in a disk of material. And not only that, they're very young stars, but closer to the star, we can resolve this even better, there's less material than further from the star. In other words, the density of the material decreases as we go close to the star and increases as we go further out here. What's that about? We think that in our own planetary system, the planets nearest the sun formed first, aggregated this material. And so if that is happening here, then the material near the star would be all clumped together and forming the first planets. So it would be scattering less light, is what I want to say, and that the material further out from the star at the edge of the disk would not yet have formed planets. In other words, we think because of that we're actually observing, not in much detail, but we're actually observing planets being formed about other stars. There's every good indication that that's what we're observing. At any rate, let's jump again. We know about one star planets did form, and this little grain of sand came to be formed. It's very precious to us. It's our Earth. But it happened not by miracle, but the normal process of star formation and planet formation. But a magnificent thing happened, and we don't think about this enough. On this planet, for the only time, as far as we know, but our knowledge is very, very limited, and perhaps for the only time in the universe, this happened. We were able to put the universe in our head, in a very real sense. How can I stand here and bold-facedly tell you that the galaxy measures 100,000 light years across? I mean, it'd take 100,000 years going at the velocity of the light to walk across that galaxy. How did I measure that distance? And how can I tell you that there are 100 billion stars in our galaxy? I can't go out and count those stars. There's no way. But I can measure the rotation of that galaxy. I can apply the law of gravity and say that rotation curve requires that there be a certain mass in that galaxy. Then I can measure the mass of the sun, and I can divide that and say, if the total mass is this and the mass of the sun is that, then take 30% of the masses in gas and stuff. The rest is so many stars. And what I'm saying is I can apply the laws of physics and use mathematics to put the universe in my head. This happened, let's say, at about the time of Galileo, the 16th and 17th century, the birth of modern science. We don't reflect upon it enough, that at least this one time, perhaps other times, the universe has become self-reflective. In us, the universe can think about itself. It's no longer sort of a blind process, so to speak. Call it what you will. I'm not sure I know what intelligence means, but at least it's a process of self-reflection whereby we can study physics and mathematics and all, and we can come to understand the universe. So the universe in us is self-reflective, is self-understanding. And that's a magnificent thing. So when we began to self-understand, to self-reflect, let's go back to galaxies again and think about some of the problems that we're thinking about today. Where did this thing come from? How did this happen in the universe? I've told you that looking further and further out in the universe, we're looking back in time, but we have never seen the birth of a galaxy. How did it happen? Now, talk about ignorant. You know, we astronomers give the impression sometimes, physicists, scientists in general, we know it all. If you ask someone to build you a house, and then you heard from your neighbor that the guy you hired to build your house doesn't know what a brick is, you'd be in trouble. But these are the building blocks of the universe, and we don't know where they came from. We frankly do not know whether globs of material first formed stars and all this, and then it came together to form a galaxy, or whether a big supercloud formed and then stars formed within that and eventually built up a galaxy. We don't know whether the process was from outside in or from inside out, so to speak. We really don't. But we're trying to understand. So we look further and further out in the universe. What is this? I mean, this is unglamorous as can be compared to those beautiful clouds collapsing and forming stars and all that. But this is a marvel. On this one photo, there are hundreds of galaxies. You can see some of them, kind of odd-shaped. But some of these pinpoints are also galaxies. And how do I know that? By measuring their velocity. They are moving so fast that they have to be very distant objects in the expanding universe, so they have to be galaxies. So take my word for it, there are hundreds of galaxies on this one slide. Well, this is as dull as can be, except for the fact that there are 1,000 galaxies on this one photo. This is some of the pictures that Hubble took of galaxies as distant as 8 to 10 billion light years. So something like 4 to 5 billion years after the Big Bang. Very young, so to speak. And there are different shapes, etc., of these galaxies. And this is the coup de grace. Hubble Space Telescope photos of the earliest object, of the youngest objects we know in the universe. And we think they're proto-galaxies. We think. I still insist we really do not know how galaxies were born, but we're beginning to get a hold. We think these clumps, by gravity, come together and build up. You can see two of them here getting together to form a galaxy. We think. In other words, it's the bottom up. Clumps of material come together to build up a galaxy, like you could take bricks to build up a house. Okay? What is this? Is this Orion come back to roost again? Is this our God out there in the universe? This is a drawing. It's not a photograph, but each point here represents a cluster of galaxies that has more than 1,000 galaxies. Now imagine. Say that to yourself again. Do you see? There's a hierarchical building up. The sun has a planetary system. Okay? Then all the stars with the sun, the 100 billion, make up a galaxy. But then galaxies form families. We happen to belong to a group of about 30 galaxies, our Milky Way, that are all bound together by common gravity. But there are clusters of galaxies that have thousands and thousands of galaxies all bound together. They're a family of galaxies. Okay? And each one of these points here represents a cluster of galaxies that has at least 1,000 galaxies in it. And the point of this is to show that they're not distributed homogeneously. They're big voids, and this is called the Great Wall. It's not the Great Wall of China, it's the Great Wall of the universe. A lineup of galaxies. What is this all about? This is the universe on a very large scale. And some suggestion is that there were secondary Big Bangs, or let's call them little bangs since they're secondary. We had the Big Bang, the universe began to expand, and then within that expanding universe, these voids were developed by secondary explosions, secondary bangs. so to speak. Don't imagine it, however, as an explosion. In fact, that's a bad name for it, Big Bang, but that's all right. That's what it's called. Well, I'm going to step out a little bit from being a scientist, because that's why I am, okay? And if you don't believe me, I can take off this collar. But I also have another interest, obviously, you know. I have an interest in asking at least the questions, if I don't have the answers, that lead, what I've said so far, that lead me on to ask further questions about how did this all come about? Did it happen by chance? Was there a purpose in it? Is there a design in all of this, you know, generations of stars and making the chemical elements and you and I coming to be, or did it? Well, let's review, first of all, very quickly, what we know happened, okay? This is age in billions of years, and this is distance. So all this is saying, as time goes on, the universe expanded. Things got more distant from one another, okay? That's all it's saying. And this curve is just, you know, an artist's depiction. It's not intended to be exact. It's just saying as the universe went on in age and expanding, it wasn't a constant expansion. The expansion is slowing down. But that does not mean it'll ever stop. It could go on infinitely, slowing down but never stopping, okay? And that's one of the big problems in modern cosmology. Will the universe expand forever or collapse again? But that's a separate problem. So, in this expanding universe, various important things happened, okay? The universe cooled down so that atoms could exist. There were no atoms in the beginning. It was too hot to have atoms. All the things that make up an atom were separated due to the excessive heat. Atoms formed, then galaxies formed. This we don't know, whether stars formed first and then galaxies, but we put it there. You know, ignorance is no stop to us, you know. Just switch this around and we're still moving. This we know pretty well. The solar system formed after about 10 billion years, and the first microscopic life forms came to be after 12 billion years. Why did it take so, if you'll pardon my French, damn long to form, you know, an amoeba? Simple little beast, it took 12 billion years. And why? I just told you why. One reason why is we needed 3 generations of stars, and the sun is 5 billion years old, so even overlapping generations, we needed that much time to get the chemical elements to form an amoeba. We didn't have the material to make them until stars did it. And then you have the rest. Here we are now, okay? This is when the sun will become a red giant star, and, you know, we'll all go with it. Now, my question is a very direct one. The classical argument, did all this happen by chance or by necessity? Let's put it in very simple terms. And I believe that the question is wrongly put. Before I address the question and think it's wrongly put, I put this on here to raise what is a modern-day argument among biologists, okay? And I'm not a biologist, so I'm not the one to resolve it, and it's not resolved. In the evolutionary process, was there a passage in evolution from one species to another? You know, were my ancestors monkeys in the real sense of the word? Was there a direct line from monkeys to more developed, and then hominids, and then me? That's very arguable. The thing you cannot argue about, whether you live in Kansas or not, okay, is that evolution is the process whereby you and I are here, and whereby the universe is the way it is today. There's no doubt about that. I mean, they shout about it. I'm going to start preaching. They shout about, you know, you have no experimental evidence. Astronomy is not an experimental science. It's an observational science. I can't touch what I'm talking about, but I know what I'm talking about. Just because I can't put it on a laboratory table doesn't mean I don't know. I have strong evidence. I've given you just some fragments of it this evening. You would not be here if stars were not born and died. There's no way. There's no way to get to chemistry. And that's what I mean by evolution. The debate as to whether one species evolves into another is another debate. And to me, for my purposes tonight, it's inconsequential whether it did or didn't happen that way. Did the human brain come to be through this process? It came to be, and it came to be by a process of evolution in the universe. Whether it evolved through these more sophisticated forms of animals or not, I'm not going to say yes or no to, because I don't need to. For tonight, all I need, the human brain did come to be by an evolutionary process in the universe. Okay? Now, did that happen by chance or by necessity? Well, let me first of all, see, I'm keeping asking that question, and I'm going to try and answer it. Take us and everything else in the universe and measure it. Just measure how big it is. That's what R is. My head is 5 inches across, okay? And it weighs, this is mass, and it weighs a certain amount, so I put it on here. I take a tree, and I measure its size and its weight. Let's call it weight. That's not exact, as you know. And let's do that with everything, including the universe. How big is it, and how much does it weigh, and plot it. And this is what you get. Now, for you mathematicians, this is a log-log plot. That means it's an exponent, because we're going from the proton to the whole universe. And so the size and mass are changing by such a large amount that I have to squeeze the picture down. I'm not doctoring the picture. I'm just squeezing it down mathematically so I can put all these things on one picture. But look, it's neat. There's nothing here. There's nothing there. They all kind of line up. Well, there's some obvious reasons for this, Like the human brain can only be a certain size for a certain mass because it would explode otherwise. The human brain generates energy, okay? If it were too small, it could not dissipate that energy enough, okay, and it would blow up. So there's certain just physical things that say you can only be a certain size if you have a certain mass, but it still is marvelous that, and my reason for using this is all life forms from DNA molecules on fit along this line. There's no exception. Now, granted, these are not, real swinging parameters, I'm not talking about being intelligent, and I'm not talking about how much you weigh and how big you are. But nonetheless, all life forms fit into the picture. This is circumstantial evidence, but it's some indication that we're part of the universe. We came out of it, we're evolving with it, according to our physical parameters. And look at this, a little more complicated, but not too complicated. I'm taking memory capacity and comparing it to taking this data that I memorize and juggling it around, comparing one piece of data to another, computational power. Now, I'm not talking about intelligence. I'm distinctly, whatever intelligence means, I'm not talking about it. All I'm talking about is the capacity to take one piece of data and compare it to another, like we did on the previous slide, okay? And you can see, again, the human being fits in here, but we're not at the top. The elephant and the whale apparently have a better capacity than we do for memorizing and comparing one piece of data to another. Look at the smart missile is over here, because a smart missile doesn't have to be any smarter. All it has to do is where is the enemy and hit them, so you don't teach it any more than that. And look at a television channel. It can't memorize very well, okay, but it can compare pieces of data. I put the British Library because a lot of my friends are British, but this holds for all libraries. A library cannot compute as such. A library can store a lot of data, but one book can't talk to another unless you put the data into a computer, right? And then you can compare it. But my point here is only to show that with all this variety of things in the universe, the human being fits into the picture. Again, circumstantial evidence that we came out of it all. Did we come out of it all by chance or necessity? So I won't take the whole problem of evolution. I'll just say us, bring it home. Did I come about by chance or by necessity? And my argument is that it by neither or by both. There's a third element in this chance-necessity debate, and that's opportunity. And what I meant by opportunity is what I've been talking about tonight. A 15 billion year universe with 10 to the 22nd stars. Okay, I don't know how to say that number. That's one with 22 zeros behind it, stars. Okay, that old, okay, evolving, expanding. That's what I mean by opportunity. How many opportunities were there for a planetary system to form about a star? Or let's take something even much further back. Let's take two molecules that the universe is cooling down in its evolution, and so a molecule forms here and a molecule forms there. These two molecules meet one another and they try to hook up, but the temperature and pressure conditions are not favorable, so they don't hook up. So they try this billions of times. But one time, in billions of times, the pressure and temperature are just right, those two molecules form a more complex molecule. And they go dancing through the universe together, and they meet another pair just like themselves. But they meet them under pressure and temperature conditions that they can't make even a more complex molecule. But one time out of billions of times, they make even a more complex molecule. Now this process is going on over 15 billion years in a universe that has all those stars pouring out all that chemistry, okay? So the point is, sometimes things happen just by chance. It just happens that these two molecules meet one another under favorable conditions. Most of the time they don't, but by chance they do. And so you get a more complex chemistry. Okay? But there are certain processes that are necessary. Okay? I'll break this, I know. But if I throw that up, it's necessarily going to come down. That's the law of gravity. And wherever I do this in the universe, the acceleration may be different due to the mass of the object that's attracting it, but the object is going to come down. Gravity works that way. That's a necessary process. There are certain chemical processes that are necessary. An expanding cloud cools down at a certain rate. So they're both necessary processes and they're chance processes. That's what science tells us. I'm sorry, I'm not trying to preach. All I'm saying is it's obvious from our knowledge of evolution that they're both necessary processes and chance processes, but there's so many opportunities for these two processes together to build up more complex systems in the universe until we come to the human brain, for instance. The gentleman who introduced me to this notion of opportunity is a Belgian biomolecular scientist, Christian de Duve, and he talks this way. He said, Einstein, his views philosophically and religiously are not well known. He didn't have organized views that way. He didn't care to. But Einstein did very strongly insist that God does not play with dice. And he was referring particularly to those of you who know the physics, to quantum mechanics, that the uncertainty principle is not an intrinsic uncertainty in the universe. It was his interpretation of this field of physics. But it can be interpreted much more broadly. Einstein felt that the processes in the universe were necessary, that God did not play with dice. He didn't just let things happen by chance. De Duve says, Albert, I'm very sorry, you're very bright. But God does play at dice because he's certain to win, or because he's loaded the dice. He's loaded the deck. He's made the universe so prolific in its opportunities to make life that he loaded it. Now that's different than determining it. Okay? Now, the point is, whether I believe in God or not is not a scientific question. That's not a scientific question at all. But once I believe in God, what kind of God do I believe in? Do I believe in a God that set the universe going like a clock and keeps it ticking exactly according to deterministic ways of doing things, or a God that lets the universe be? It has its own dynamism. There are processes within it that not even God can control. Okay, heresy. Tear my gown. But I think that's the better scientific view, that's the better scientific view. If you're going to think of the universe as a scientist with a religious sort of leaning, I think, to my mind, that's the best way to think of it. I don't think it challenges God. I don't think it denies that God created the universe. He created it in this way. He's treating the universe like a parent treats a child. See, there comes a time when a child is no longer a child. It has to you teach a child, you discipline it, give it more good standards, but finally a child has to make up, where am I going to go to college? Who am I going to marry? What am I going to do for a living? It has to grow up, right? You have to let loose. There's a certain freedom and dynamism, I think, in the universe that God made that way. God's letting the universe loose. Do your thing. Grow up. Increase and multiply. Get more complex, make a human brain, and all of that. Well, that said, this is a depiction of what I'm talking about. This is a strange tree. It's not the tree of life. It's the tree of the universe, the whole universe. Everything that ever happened in the universe. The Big Bang, the first atoms that were formed, the first stars that were formed, the first galaxies that were formed, you and I were formed, grandchild were born. Everything is here. The deer that died last week and all this, it's all there because this is a strange tree. It's a tree of the universe, but nothing has disappeared. Most trees lose their leaves in the fall and all of this. This tree hasn't. It's kept everything that ever happened in the universe is preserved there. Now you let a nice breeze blow through from the ocean, okay, and blow off all the stuff that never worked. All those chance processes that ended in a blind alley, the molecules did not meet at the right time and place, etc. That happened billions of times. So when you blow a wind through this tree, you shake off a lot of dead stuff that never, but you still wind up with a structure. You still wind up with a structure. That is, within that universe, where many processes were not succeeding, there were some processes that were succeeding and getting ever more complex. And so you're bound to wind up with something like this. Not identically this. We put the human being, by the way, at the top because that's the best we know. The human brain is the most sophisticated piece of the universe that we know of. So we have to go on what we know. It's not putting ourselves in a favored position. It's just saying what we know. And we know this process describes very well the evolutionary track of the universe. It could be slightly different because this happened not just by deterministic processes, but by chance processes. So it's my inclination to say, I think you and I would be here, the human brain would be pretty much the way it is through this complex series of evolutionary processes, but we could be slightly different. Things could have evolved slightly differently, with hands and noses and all this stuff. So what, I live in Italy long enough, though, to know that if the human brain evolved with the capacity to speak, for an Italian, they'd have to have hands. So that would at least, I'm sorry, any of you of Italian descent, you may have noticed that I've grown. Well, that's the story that I have to tell you, frankly. I think there are many challenging things. You could challenge me on many of these things. My point is I think the best scientific view of what we know about the universe is something like what I've said. There are many cracks to be filled in, etc., but I think the general picture is that. And if one wants to think religiously about it, okay, I think, frankly, this view of the universe, this scientifically established view of the universe, enriches my faith as a religious person. It makes me all the more want to believe, because I think it's magnificent that the universe has this and continues to have this dynamism. I don't think it detracts a bit from my belief in God. In fact, it adds to it, but I'm just foisting that upon you. Finally, I was always taught as a scientist. This is my little final cartoon. No doubt about it, Ellington, we've mathematically expressed the purpose of the universe. Gad, how I love the thrill of scientific discovery. So they have this very complicated equation looking for the purpose of the universe, and of course it comes to zero. Now, I was always taught this as a scientist, that a scientist tries to understand the what happened, where it happened, when it happened, how it happened, and all of that, but not why it happened, because that belongs to the philosophers and the theologians. And I thought that was true for the longest time. In my balding days, I'm beginning to wonder about this, whether this separation between the scientist and the philosopher theologian and their fields of study is that neat and clean. I just wonder, and I leave you with that wonder. I think I've talked enough. Thank you for listening. Now, I'd be most happy to entertain, I don't always like to say questions, discussion, any of your viewpoints, or questions, provided they're easy ones, okay? And if you ask a question and I say that's a very good question, my students in Arizona can tell you exactly what I mean, because I say that many of times to them. They found out what it means. I don't have the slightest idea of the answer. Please, the gentleman with 2 or 3 fingers up like this. Yes.
Yes, thank you, Father Coyne. The one with the picture you had of the tree, with all the dead ends and so on, finally. I think for many people, the greatest objection to that might be that it seems that there's such a great mass of those dead ends, being a lot of suffering and death, etc. In other words, the problem of evil becomes a very big, I think, an issue there. And I know as a theologian too, I've wondered how do you wrestle with that?
Okay, the question is a very good one. And I really do mean that. There's really no, to my satisfaction, I've never heard a good answer. I don't have a good answer. The question is the problem of evil in the universe with respect to this, say, taking the tree and all the dead processes that took place, Little children died of leukemia. This happened in this universe. My approach to it is first of all, twofold, to make the very clear distinction that I'm sure everybody makes. But let's make it between moral evil and physical evil, okay? Moral evil is the evil that people do by free choice, and you have to have a free, choosing human being to do that. I don't think animals can commit moral evil, even though it looks terrible to see one animal kill another. But human beings can. And that, of course, is the result of human beings having free choice. That's the terrible risk, let me put it in terms of God. Making a person like me that can choose to do things, to try and kill God, to deny God, to kill my neighbor, to do all kinds of things that I freely choose to do that are clearly against what is good. Okay, that's moral evil. But physical evil, and that is explainable by simple fact, it's necessary. If a person is going to be free, you have to be free. You have to be free even to do what is evil, or you're not free. It's just the necessary consequence of human freedom, I think. But an analogy from that carries over, I think, to physical freedom. It's necessary that there be this. That's the way the universe is. I mean, it's just the way the universe is, And if it weren't that way, if it weren't for those physical evils, the human brain may never have evolved, for instance. I mean, you can't directly link a child dying of leukemia in order that I be here talking to you tonight. I don't mean to make that direct link, but the overall process towards more complex organisms in the universe requires death. It requires what I call physical evil. I think it's just a part of it. It's a mystery. I mean, I don't plan by saying that to have explained it away, because it still bothers me, that our fight against cancer never seems to really succeed in all of this. And, you hear people say, such a good person, why did God make him suffer or her suffer so much? There's no real clear answer. I think the general indication is precisely that. It's a mystery within the dynamic, evolving universe. It's the nature of the universe that these things, by necessity, have to happen Just like two molecules didn't make it. They didn't get to go to the dance because, but later on, two molecules did. How come he chose those two molecules and not me? How come the conditions weren't right when I was there? That kind of thing. It's the best I can do with a very difficult. I think it's explainable better in this view of the universe than in any other that I know, though. It's the fault of the universe. It's the way the universe is. And if it weren't that way, you and I wouldn't be here, so to speak. Please? Yes.
To clarify a point that you're making in my own mind.
Yes.
I think you would agree, and most evolutionists would agree, if we were to go back half a billion years ago and replay the tape, life as we know it on Earth today would be very different. If we were to go back to the Big Bang and replay that, would we have the same universe today, in your mind?
My answer, I think, is a simple no.
We would not.
No.
So
The universe, the way it is very contingent. It depends on certain conditions at certain times, and they could
the connection between the physical state of the universe and the existence of humans
That's correct.
are both contingent. Is that correct? If the universe were different, humans would never have come about.
If the universe were different, it's quite possible that human beings would not have come about. That's correct.
So evolution, in your sense, is directionless. Man was not destined to become part of the system.
Boy, you're going to make me commit heresy before I get on. Putting aside religious belief completely and speaking as a scientist, I like to cover my you-know-what. Rome is a long ways away, but with email and all that stuff today, before I get back to Tucson, I'll be... No, seriously. I see the universe as a scientist that life did not necessarily have to come to be, even in this universe, much less a universe that had somewhat different conditions. It was not a necessary eventuality. In other words, if I were back there, okay, obviously this is a thought experiment, at the time of the Big Bang, looking forward and knowing everything, knowing all the laws that would come to be of physics and chemistry, and all the processes that would come to be, okay, I think there's enough chance in all of the processes that I could not predict, knowing all those laws and all, that life would come to be. I don't think I could predict it. That's my viewpoint as a scientist. That there's a direction in it all. When you see this, all the leaves blown off this tree, there's clearly a direction to it all. But that does not mean that God planted the tree and determined that it would grow in this way towards human life. He didn't determine it to happen that way.
Your tree is somewhat misleading in that your branch for single-cell organisms, for example, is still quite low.
Yeah.
They exist today.
Yeah.
They should be going up.
Yeah, that's correct. Yeah.
So your tree is not...
The full skeleton tree exists today. All those branchings still exist. But everything that's from the bushy tree to the skeleton tree, okay, everything else died off, every other process. In other words, you would expect chance processes. In fact, you can make, mathematically, you can make some wild guesses at how often a given process succeeded against not succeeding. And the successes obviously are very low at the beginning. Once you get more complex, then there's a built-in drive, a built-in dynamism because of the more, just talk chemistry. As you get a more complex molecule, it's much easier for that complex molecule to get more complex once it's at that stage. Well, look at us. Look at the human brain today. Look at our lifetime with what we've been able to do with fair ease. The whole electronics, development in electronics and communications. and weapons of war, take both sides of it all. But I still, to answer your fundamental question, my position would be, it's arguable, that human life did not have to come to be in the universe as we know it. Please?
Within this perspective and view of the universe, how do you explain the Bible or interpret the Bible?
Well, that is a very easy question when you come down to it. When you get into the details, it's not. The Bible is not a scientific textbook. I don't know of anything in the Bible any place in the Bible where it teaches science as such. I know places in the Bible where it speaks of history and it tries to be exact and it's historical. I know of places where it tells stories, myths, fables for a purpose. But I know of no place where there's any attempt to teach science. So let me say what Galileo said. Scriptures are intended to teach us how to go to heaven and not how the heavens go. And that's the answer to your question. It's obviously now would require, the book of Genesis and everything else. Beautiful stories, saying much more about God than they are about the creation of the world. They're talking about God. In fact, God made the world in such a loving way that he had to rest at it all. I mean, that's what it's talking about. Read it just as a story and you'll see that. I had a very close Talmudic scholar friend, Jewish friend, who was a physicist, and we were debating in this way. And he was a very fundamentalist Talmudic scholar, and so he's, I told him, I said, well, if you really take, there are two Genesis stories of the creation of the world, by the way, and they contradict one another in some small things, okay, because they're two different authors telling stories, so they're bound to, but in one of the accounts, God made light on the first day, and he made the stars, the sun and the stars, on the fourth day. So my question to him is, where the hell was that light on the first day? We know all light comes from the sun and the stars. And he looked at me seriously and he said, the first day was the cosmic background radiation. When we get at that stage, I just, give me another beer. I don't mean to make fun of that, but that's one, it's an attitude towards Scripture that I share not at all. Please, you have tried several times.
Yeah, you stimulated so many questions that I'm frankly at sea. One, when you said about the tree, there not being necessarily the tree of life and so forth, but that these things came about, and we can see them, we can see the structure of the universe so that we know of, et cetera, et cetera. But you then concluded by saying it is not necessarily the universe in which humans had to evolve or had to appear.
Correct.
That to me is a very directed statement that there is someone, the big finger says they will appear.
Okay, very good. I'm glad you brought it up. So this discussion now has said that I've introduced a degree of confusion into the whole thing, and I accept that, because I've said on the one hand that we have this tree of life, this tree of the universe. It's not a tree of life. And that when I shake off all the unsuccessful processes that happened in the evolution of the universe, I find this certain direction, this trunk that goes up to more complex. But I still deny that life, human beings, would have to come to be in the universe. In other words, that trunk could be quite different. Or it would have to be some kind of trunk there. I mean, statistics tell you that determinism will drive this. Some of the processes are deterministic. There's a lot of casual processes too, chance processes. But you're making now a very good point saying, but, you know, since the human being is there in a process where the human being didn't have to be there, according to what I've said, I've taken both positions, human being didn't have to be there, but we're here, okay, then I must, in order to be, you know, a sane, rational human being, I must say that there's someone who determined that the human being would be here. The human being didn't have to be here, and yet the human being is here, and someone said the human being has to be here. And I don't accept that, and yet I hold on to my religious faith. I look at God as a being who wanted the human being to come to be. Now, I don't know what I mean by that. I'm struggling with this too, but I find it very difficult scientifically to accept the God that made the human being come to be. I really do scientifically find that difficult, and yet it doesn't challenge my religious belief. The human being did come to be. God is delighted that the human being came to be, and he's helping me be a little bit better all the time. But I don't think in order to hold on to the notion of God that I have to see God as a person who made this happen by his own sort of determination.
One more thing. The scientific approach is basically a process of reductionism. And, you know, we get to the little ones, the little ones, the little ones, and so forth, and our logic follows that sense. The idea of faith is, to a religious person, hardly tenuous. It's got as much teeth in it as any reductionism ever had, which is probably why science and religion have been doing this. But I think that your point of view will bring you to the answer of there being a supreme being, either way you go. And I believe the way to do this is, like Anselm said with the first Archbishop of Canterbury, don't try to understand so that you can believe, but believe so that you can understand.
That's very good. I accept that completely. I hope you all heard that. I mean, his point of view, and it's a point of view, I mean, nobody can prove it, is that when you're talking about science and religious faith, let's not call it religion, we can call it different words. I think of it as religious faith, because religion is practice of my religious faith. And I can have faith and not practice. I can practice and not have faith. I mean, the sisters beat me to go to church. And so I went to church. That did not mean I believed. But I'm getting off the point. The point is St. Anselm, you know, believe that you can understand. Don't expect understanding to bring you to belief. Accept that completely. I mean, I can say of my own personal, and it's very personal, but I think it's shared by many others. You know, I did not come to believe in God because of science or any other rational process. I came to believe in God because my parents did, and my brothers and sisters did, and they brought me up that way. And when I grew up, I challenged it, and then I found out there was no reason not to believe, that it enriched my life to believe. And I found out that there were good reasons to believe, not ultimately convincing reasons, but good reasons to believe. I wasn't giving up reason in order to believe, but it's that religious faith went beyond anything I could reason to. But once I accept religious faith, I can honestly say all of my science has contributed to my belief. It's given body to it. It's given some substance to it. It's giving some more meaning to it, and it's never challenged it. I think the science religion, I like to think of it as science faith dialogue is the better way to put it. They've only gotten in trouble when one is ignorant of the other. The church, ignorant, absolutely ignorant of what Galileo was trying to do. No doubt about it. History makes that very clear. For good reasons, the church condemned a renowned international scholar who didn't have proofs and never claimed to have proofs for the heliocentric system, but had some damn suasive evidence. When you get a scholar today who has good evidence, you shut your mouth and let it go on until the discussion matures. If he's a renowned, respectable scholar and is working on a problem and has good evidence, you don't shut him up. I mean, that's to me, that's what academic freedom is all about, that you allow an intelligent process. And what the church did, and Galileo, well, we're getting way off. Galileo tried precisely that, to tell the church, don't do anything. You don't have to. You don't have to pronounce on this issue. It's not going to save anyone. It's not going to condemn anyone. It just let it be. Let us get on with our telescopes and find out what's really happening. Why do you have to step in? And so the church was ignorant of what science was trying to do, and the opposite has happened. I mean, to me, Dennis, I really do. I'm a great fan of Carl Sagan and all, but I think Carl Sagan, may he rest in peace, I think could be, he's not here to defend himself, accused of that other, of a certain scientism. If you can't prove it by science, then God doesn't exist. I could never prove God's existence to Carl Sagan or anybody else, including myself. Prove it. Cinch it. Like I can the size of our galaxy. I can't. Please, sir.
Getting on another subject, as we're expanding, the gravitational pull on each of the units would seem to be lessening by the square of the distance. Why should it be continuing to expand, as some are talking about? There's a body of evidence that suggests it's not slowing. Why do we need to even talk about the fact that it is slowing? What is there besides gravity that would cause it to decelerate?
Yeah. So the question is, the expanding universe with the law of gravity, since the law of gravity goes as the inverse square of the distance, things are getting further away from one another, so the gravity pull on them should be decreasing with that. And therefore the universe should be slowing down, according to all of that argument, in its expansion. And that's what we thought was happening until some recent observations that indicate some very distant objects, but it's only, I use the word indicate, that some very distant objects are overcoming this diminution of gravity. That is, they're going faster at the very edges of the visible universe than they should be according to the law of gravity. So we're coming back to thinking of a sort of reverse gravity, of a repulsive force between. Please?
I misunderstand what you're saying, because it seems to me that as the gravitational pull gets less, there would be more acceleration, because we're talking about a bang, the projectile's going out, and the only thing that's pulling them back is gravity. But if the gravity is getting less of a pull all the time, then it's going to accelerate outward.
No, it wouldn't cause, it would not bring about acceleration, because the amount of energy in the universe is finite to use. Let's not call it an explosion. The Big Bang released a certain amount of finite energy in the universe, okay? And that's being used up with the expansion of the universe, right? And it's finite.
Do we know it's finite?
What we've been able to measure is finite. We don't even know whether the universe is finite, so we don't know whether the universe is finite or infinite. I'm talking about the visible universe, and that's certainly finite by definition. So I see your concept that if distance is increasing, gravity is pulling less, so those objects, they're being pulled in less, they should be expanding faster. No, the reason they started expanding at all was because of a finite amount of energy being released. In other words, is gravity going to win out, or the intrinsic energy of the universe going to win out? Is the war. The war is between gravity and this intrinsic energy that's expanding the universe. Yeah.
You said that God set the universe up and then can't interfere in some of the processes. So Christianity is based on faith in a miracle, which is the suspension of physical processes, right? So how do you mesh those?
Yeah, I don't. Yeah, that's a big challenge. So the question is miracles. How do, certainly the Catholic Church believes in miracles. We canonize saints, and the only reason they can be canonized is they work 2 miracles at least. They're authenticated by medical examination and all of this. I don't. It's difficult. I don't have an answer to that. Because the point is that seems to contrast with my notion that God does not intervene in the universe. He's not a God who puts his finger in to touch things up when they need touching up. I would have to admit by exception, if I believe in miracles, publicly I do. Publicly I do. I certainly believe in the miracle of Jesus' resurrection. I do believe in that, because if I don't believe in that, I'm done. So I do believe in it. I have trouble, frankly, with other miracles, I'll admit it. But publicly, I do believe in miracles.
Even the birth of Christ is miraculous.
Yeah, the birth of Christ. All things that happen to Christ in that way, I really do believe in. But it is faith. And I have some trouble with it. Faith is not something you just have. You have to faith has to be lived, and you have to think about it every day and try and make it consistent with new scientific results and all. But I do not deny the virgin birth of Christ or Christ's resurrection or any of the key, what appear to be miracles. See, I'm trying to make it easier on myself saying appear to be. I'm in trouble. I am. She's still smiling. Yeah, let's swing around a bit. This gentleman here. Dennis, you must tell me when.
I have a question, and your last statement you said about religion versus science. And what I've been thinking lately is that the two are kind of proving each other, that the laws of nature, in essence, are God's kind of rules set down to us. So I was wondering what you thought about that, if you thought that over time that these are coming closer, and that's why I don't see them I don't see science and religion fighting each other quite as much.
Yeah, good. The point that the young gentleman is making, science and religion, he doesn't see that much contrast between them. In particular, if you think of the notion of the nature of the laws of nature, that there is, within the scientific thing itself, there's this rational process of the laws of nature at work. And why should that contrast with a belief in a God who made a universe that has these laws of nature? I think that's the kind of approach you're taking. And I like that very much, but I find, I have to reveal my ignorance. The laws of nature, that very concept, I sometimes wonder about. What do we mean by the laws of nature? Is it statistically that we've observed that every time I have this, I have that? Or do I think that it's an intrinsic working? I said if I throw this up, it's going to come down because the law of gravity is that way. Let's examine that more. What do I mean by the law of gravity is that way? What is that? Is that necessary to the nature of the universe? Or did I think that up from my observations and from my analysis? Did I create, as a physicist, the law of gravity, or is the law of gravity out there in the universe? I'm not sure. But I think we also better, Dennis.